The first one by Ariana Di Cinti and the second one by Malcolm Longer. This first one, well, Ariana is a well-known world expert on galaxy simulations, and in particular on the modeling of the baryonic feedback. And this is very interesting, I think, about related to what we're discussing here, because it's something, some effects, as she will tell us, that might be degenerated with our understanding or extraction of dark matter parameters. So, thank you.
Yeah, thank you. If the lights can be put down a little bit so we can see videos and stuff. So good afternoon, everyone. It's a great pleasure to be here. Thanks for the invitation to come. I work at the Instituto Astrofísica in the nearby University of La Laguna, and I'm going to talk today about simulation of galaxies. So this is going to be the outline of my talk. I will start with a brief introduction on galaxy formation. Then I will move on talking about N-body and hydrodynamical simulation, explaining why we need simulations to study galaxies. And then I will dig a little bit in deep detail about the physics involved in hydrodynamic simulation. Then I will move on towards the end of my presentation on showing you some famous example of state-of-the-art hydrodynamic simulation. And finally, at the very end of my talk, I will tell you how to run a simulation on a supercomputer. So this is how to make a galaxy in one slide. I don't know if many or most of you is familiar, perhaps, with this, or if you are maybe particle physicists. So I just want to make sure we all know what we're talking about. What we need to create a galaxy is, first of all, we need to form particles in a Big Bang. So we need to form the first particles, which are essentially hydrogen, helium, and dark matter. Then we need some tiny quantum fluctuation to cause some region in the early universe to be denser or over-denser than other region. This region will start collapsing under their own gravity, and they will form what we call dark matter halos. So in order for structure formation to proceed, we actually need a lot of dark matter. We'll have then gas that flows and gets into this dark matter halo, and when the gas met certain condition, particularly when it gets cold and dense enough, it will fragment and form stars. And this is how we form the first stars in the universe. Then, of course, we have stellar evolution, so stars evolve depending on their mass. They can explode as supernovae, and they release into the surrounding gas a lot of energy and a lot of metals, which are all elements heavier than hydrogen and helium. And so this is the way in which we enrich our intergalactic medium of metals. And at the same time, while all of these processes are happening, the universe is expanding, okay? So we need dark energy for that. And what's happened at the same time is that this small initial dark matter halo will start collapsing and merging into each other to create bigger and bigger structures until creating the biggest galaxy clusters that we observe today. So let me go a little bit more in detail. As I say, this is a sketch of how galaxy formation proceeds. So the idea is that you start with a Big Bang. At the very beginning, the universe was a hot and dense place. After that, we went through a phase called inflation, and after the inflation, the universe became much cooler, full with a plasma made of hydrogen and helium, and, as I say, also full of dark matter. In a cold dark matter universe, while the initial density distribution was pretty much homogeneous, there were small overdensities that can, under their own gravity, collapse and clump together and form what we call dark matter halos. So when I talk about dark matter in structure formation, I like to make this point because we all know, I guess most of you know, that there are many indirect proof of the existence of dark matter. For example, galaxy rotation curve, or you can look at the Ballet cluster, many different things. But in particular, in a structure formation scenario, it's important to have dark matter in order to create all the structure that we observe today. So if you have a universe made only of baryonic matter, which is atoms, quarks, electrons, all the regular matter we know about, we will not have enough time in 14 gigayears to evolve in such a way to form all the structures we observe today. So we actually need dark matter to give a good kick start, let's say, to formation, to forming the first structures. So galaxy formation is believed to proceed from an initial creation of these dark matter halos, and we can actually calculate and compute what is the matter density and the matter budget in the universe by using experiments such as cosmological ones. For example, the Planck satellite. There was a ESA mission. In this pie chart over here, you can see that about only 5% of the total matter density in the universe is what we call baryonic matter. In astrophysics, baryonic matter includes also leptons. So it's quarks, leptons, atoms, anything we know. And then we have about a 27%, which is dark matter. And the remaining 68% is what we call dark energy. We should not be confused with dark matter. Dark energy is a form of energy that we need in order to explain the accelerated expansion of the universe. Okay, so what is dark matter, by the way? Well, we think that dark matter is a form of matter, is a particle that does not interact gravitationally, does not interact electromagnetically, but only gravitationally. So it does not emit or receive electromagnetic radiation, and this is why it's dark. This is why it's called dark. And so it interacts only via gravity, and is a collisionless particle. So as I say, at the very beginning in the early universe, we have some areas that are denser than others. And we can actually measure this, again, by using cosmological experiments. For example, this is a Planck satellite. And we can measure what is called the anisotropy temperature map of the CMB, of the cosmic microwave background, which is a relic thermal background from the Big Bang. And so this temperature map is telling us that the universe was homogeneous, but with small patches of not homogeneous places. For example, look at this cooler area in blue, and these are slightly hotter area in red. And what they're telling you is that they are a representation of this initial over and under dense region. So in fact, in galaxy formation, we can take this experiment and calculate our initial condition to start a simulation. Okay, so then the first dark matter halos collapse. They form first very small clumps, and then they start merging together, which means collapsing together to create bigger and bigger structure. And so the idea in a hierarchical galaxy formation model is that you have the biggest galaxies into the biggest dark matter halos, and the smallest galaxy, like dwarf galaxy, into the smallest dark matter halo. So if your dark matter particle is cold, which is the current cosmological paradigm, you expect galaxy formation to proceed this way. So you form the smallest galaxy first, dwarf galaxies, and as they clump and merge together, they create bigger galaxies, and all the way to cluster of galaxies. So in fact, cluster of galaxies are the most recent structure in the universe. And this is what we call a bottom-up scenario. You go from the bottom, you first create small scale, and you build up through merger bigger and bigger objects. So in fact, structure formation depends strongly on your dark matter particle type. And because this is a school connecting astrophysics, particle physics, and cosmology, I'd like to mention this. So the current cosmological model is what we call lambda CDM. So lambda, the cosmological constant, plus cold dark matter. Within this model, dark matter particles are believed to be very massive, of course, massive in terms of, particle masses. So they are tens to hundreds of times the mass of a proton. And they're slow moving meaning that they're not relativistic. And so if this is the case, if the particle mass is of the giga to tera electron volt, the structure formation happens just in the way I told you, bottom up. You form small clumps first, and then they merge together and create larger galaxies. And this would be a final redshift zero simulation of a cold dark matter scenario. You have a central galaxy and a lot of small clumps around it. What happens instead if your dark matter, let's say, is hot? Hot dark matter is a particle that is very light and very fast. So it's got a relativistic speed. Well, in that case, what happens is, at the very beginning, when these perturbations are growing, this hot dark matter is able to cancel the small perturbation. So it means that you never form the smallest dark matter halo. You directly form big objects. And later on, by fragmentation, you can create smaller galaxies. And so we can measure real galaxies, look at their ages, and we know that this is not what happened. So we know that most of the dark matter in the universe cannot be hot dark matter. This is why we cannot use neutrinos as the only form of dark matter. So we know that most of the dark matter in the universe must be cold, or perhaps it could be warm. So warm dark matter is an interesting alternative. It's made of fast-moving particles with masses of about kiloelectron volt, and essentially gives you the same predictions as a cold dark matter model, but it creates less small clumps. You see, if you compare this image with this image, we have less what we call satellite halo around the main galaxy. And so this is a way, in fact, to put constraint on the world dark matter particle mass. You can look at our own Milky Way or other galaxies. You can count how many subhalos or satellites you have around, and then you can put constraint on the world dark matter mass. Okay, so that was just the introduction. Now the question is, why are we actually here today? Why do we care about simulation of galaxies? Why do we do simulations in the first place? The reason is very simple, that galaxy formation is a highly non-linear process. It means that while at the very beginning, the density contrast in the early universe, it actually grows linearly. So at the very beginning, we can follow the evolution of the overdensity with a pen and a paper, just doing equations. Very soon after that, the density perturbations start growing in the nonlinear regime. And so the only way we have in order to study how galaxies form is by running simulations. So the simplest simulation you can run is called a dark matter-only simulation. I think you might have seen it in another lecture. Dark matter-only or embodied simulation. So when I say embodied or dark matter-only, I mean the same thing. It's a simulation in which, in your box, we only have particles representing dark matter. They are collisionless, they do not collide, they interact only via gravity. So we need to solve an embodied problem. And then more sophisticated simulations include, of course, gas and stars, which after all is what we see in the universe, and all the relevant equations of hydrodynamics. Okay, this is a slide showing you a lot of recent simulation methods and codes. So over here we have embodied or dark matter-only simulations that, as I say, proceed via collisionless dark matter-only particles. And then depending on your gravity solver, so the solver you use to calculate your gravitational force, you have different of these codes. You have like gadget, PKD grav, and so on. On the right side, we have hydrodynamic simulation. And they divide themselves into two big groups. We have particle-based, which are called Lagrangian methods, and grid-based, which are called Euclidean methods. So within the particle-based, you have this SPH, which is smoothed particle hydrodynamic. This is a solver of your hydrodynamic equation, and some famous codes that use this solver are gadget and gasoline. And then you can have some moving grid or adaptive mesh refinement codes, Ramses, and so on. I just want to stress out here that when you solve an embodied-only simulation, you just calculate the force of gravity. And when you do an hydrodynamical simulation, so you include your gas, you have to solve the equation of hydrodynamics for your gas, but you still have your dark matter on top. Okay? So you still have to solve for the force of gravity. So in embodied-only simulation, what we do is very simple. We start from the Poisson equation, which connects your density field to your gravitational field. We solve this equation using a particle approach, and we essentially calculate the numerical solution of the equation of motion for an ensemble of n particles interacting gravitationally. Okay, so each particle feels the gravitational effect of all the other particles in the simulation. We evolve this ensemble of particles just using gravity, and we see what happens at redshift 0. So one important quantity that I want to mention is what we call the softening length. I want to mention it because it also happens in hydro simulation. The softening length is this epsilon constant here, and that we put in the denominator of the force equation, and essentially it helps you at avoiding singularity when two particles get too close to each other, and it effectively sets the smoothing mass, and it sets the maximum force resolution of your simulation. So if you run a simulation with a softening length of, let's say, 1 kiloparsec, it means you cannot go and look at the simulation inside this region. That's the maximum resolution of your simulation. Okay, so let's try now to do our first n-body-only dark matter simulation. What we do is we take a box, which should represent a part of your universe. We fill it up with particles, dark matter-only particles. We impose initial conditions on this simulation, which means imposing the initial over-density and under-density field. And then we run the simulation all the way through redshift 0, just using gravity. And what we see is that from an initial distribution, almost homogeneous, you start collapsing regions, and they clump together to form filaments, knots, walls, which is what we call the cosmic web. Right? So within each of these bright spots, which is a dark matter halo, we are supposed to find galaxies today. So once more, I like to point out that when we put dark matter particles in a simulation, of course, we don't have the resolution of a proton. Okay? So when we put dark matter particle, the state-of-the-art highest resolution simulation puts something like 10 to the 5 solar masses for one dark matter particle. So really, your dark matter particle is representing a whole phase space of dark matter. Okay? Remember that. One interesting technique that we can use in simulation is called the zoom-in technique, and essentially allows you to resimulate an initial box with focus, particular focus on one dark matter halo. So how it works, you take your simulation box, you run it to redshift 0, you then identify your preferred favorite dark matter halo, you identify the particles back in the original box, and you resimulate it, increasing the resolution only in that area. So in this way, we can have very high resolution dark matter halos without being too much computationally expensive. And this is called the zoom-in technique. And of course, at the end of the simulation, we have this beautiful thing, which is a time snapshot of galaxy formation that you can directly compare with your observation, with the real universe. So what you can see here in these boxes is a simulation of redshift 10, 6, 3, 2, 1, 0, and you can clearly see the bottom-up formation of galaxies. So you start by forming the smallest clumps first, and as they merge together, they create bigger and bigger structures. So the beauty of simulation is that it allows us to study the evolution of galaxy across cosmic time, something that is very difficult to do just with a telescope. And so in the last couple of years, the advances in computer power and technology have allowed to perform very high resolution simulation in large boxes. So it means that we can simulate a large volume of the universe and at the same time resolve individual galaxies. So this is the resolution elements in your simulation as a function of the years. And so the very first hydro simulation run in the 1995, that's something like 10 to the 4 to 10 to the 5 particles in total, which is ridiculously small compared to nowadays simulation that have order of billions. Okay, so the doubling time of this curve is approximately of 20 months. And so to conclude the n-body part, I'd like you to show this beautiful image of the Millennium simulation, which is one of the biggest dark matter-only simulation ever run. I think probably the biggest. It was run using the code Gadget. It contains more than 10 billion particles to trace the evolution of the matter distribution in a cubic region, which is super large, about 2 billion light years on a side. And so you can see this image is zooming in more and more towards a specific region of the universe. Now we are about 62 megaparsec. Remember that our local group is something like 5 megaparsec. So you can see the level of details of this simulation, and you can see that they predict these filaments and webs, which is the cosmic web. Again, this simulation was run in a cold dark matter framework. Okay, let's now move to hydrodynamical simulations. As I say, on top of dark matter, now you have gas, and gas eventually will form stars. So gas is a fluid, can be interpreted as a fluid, and so to know the equation of motion of this gas particle, we need to solve hydrodynamic fluid equations. What we want to do in a simulation at every step is to compute where each particle goes. Okay, you have your box with position and velocities of each particle, and at the next step, you want to know where each particle went to see if it creates a galaxy or whatever it does. So on top of solving hydrodynamic equation, of course, there are a bunch of things that happen in a simulation, which we call the subgrid level, so below the level of resolution of your simulation. And we're going to talk about this in a minute. Okay, so hydrodynamic simulation can be divided, as I mentioned before, into big groups. Grid-based or Eulerian methods are those methods that treat the particle as a continuum and essentially develops all the equation on a grid, as in this area over here. And instead are particle-based or Lagrangian methods in which we follow the motion of the fluid elements. We consider particles as a discrete phase and we track the pathway of each individual particle. This is another example, visualization of a Lagrangian method in which we essentially are moving with the fluid. But anyway, either way, well, let's say for a moment that we want to write and solve the equation of motion of an ideal gas in Lagrangian form. What are the equations you need to solve in order to calculate the position of your gas particle every time? The four main equations. You have the Euler equation, which represents the acceleration of a fluid, so dV in dt. And this acceleration depends on the pressure gradient and on the gravitational field, this phi over here. You have the continuity equation, which, as you know, describes the conservation of mass. You have the energy equation that follows directly from the first law of thermodynamics, which is the law of conservation of energy for closed isolated systems. And it describes the change in energy as a function of time done by the adiabatic work on your fluid element. And finally, you need a closure equation, which is your equation of state, this one down here. Okay? And it relates quantities such as the pressure to microscopic fluid quantities such as density or temperature. So these are the hydrodynamic equations that your solver can do, can solve for you. For example, you can use a SPH method or Eulerian method or whatever you want. I would like now to move to what are the actual physical processes that we implement into hydrodynamic simulation, okay? Because when we run dark matter only simulation, it's pretty simple. We don't put anything in, just gravity. But when we include gas, we want eventually to form a galaxy. So what are those, we call it baryonic physics processes that we input into hydrodynamic simulation? Well, first of all, remember the gas cools at the center of your dark matter halo, and in order to be able to form stars, it has to become dense and cold. The way in which gas becomes cold is via cooling processes. There are various types of cooling processes, such as Bremsstrahlung, collision, and in general, we can describe them using what is called a cooling function. A cooling function is what I'm showing here. On the vertical axis is lambda, which is a cooling function, as a function of temperature in Kelvin. So the cooling function is the units of erg per second normalized to the volume, centimeter cube. The cooling function represents your change of internal energy of your gas per time, just by the gas losing energy via radiative processes. So the bigger is your cooling function, the faster is your gas at cooling down, okay, at becoming cold and eventually forming stars. So this here in black is the cooling function, in dark black over here is the cooling function for primordial gas, which means gas including only hydrogen and helium. And you can see that he has two main peaks, one at about 10 to the 4, which correspond to the ionization temperature of hydrogen, and one about 10 to the 5, which is the ionization temperature of helium. Above 10 to the 5, hydrogen and helium, which I remind you are the only two elements in primordial gas, they're fully ionized. And so above 10 to the 5, the main mechanism to cool down ionized gas is Bremsstrahlung. And so all the other curves that I'm showing here, increasingly, are curves of increasing metallicity. So you go from primordial gas to a gas that has a solar metallicity, like this one, to a gas above solar metallicity. And what you see is that your cooling function increases. Okay? So it means that at a fixed given temperature, your cooling rate is higher for higher metallicity. If your gas has been already metal enriched, for example, by supernova explosion, is much more able to cool down. And you can see here in the right plot what is the contribution of each element to the cooling function. And you can actually see that most of the elements have transition line at about 10 to the 5 Kelvin. So in general, remember, to cool down your gas, in the simulation, we input some tables, we represent your cooling function, and for high metallicity gas, you can cool down faster, and also if your gas is denser, you can cool down faster. So at a fixed temperature, dense gas and high metallicity gas cools down fast. Okay, once the condition to form stars are met, we want to now form the stars. Just like for a dark matter particle in the simulation, your single individual stellar particle does not represent one star. Your stellar particle is like 10 to the 4 solar masses. So your stellar particle actually represents a star cluster, a whole stellar population. So what we do is we allow cold and dense gas to create stars stochastically following the Kenica-Smith law, which I think you know what it is this plot over here connecting the density of star formation with the density of gas. This is a very well established empirical law, so we use that to allow for gas to create stars. And then, of course, we have to tell what is the IMF, what is the initial mass function of your stellar population. This is an example of IMF as a function of mass. It just tells you, for a newly born star cluster, what is the mass of all these star particles. So the IMF is very important to include in your simulation because different IMF can result in more or less massive stars, which means you can get more or less supernovae, and this is very important for your feedback. For example, a Chabrier initial mass function, which is this pink thing going down, produce 2 times more supernovae type 2 than a Kroupa initial mass function. And this is very important when you want to calculate your stellar feedback. Okay, before moving on the stellar feedback, what else do we input in the simulation is something called UV background. So you know that the universe has been reionized. We think we can measure, and we think the reionization ended around redshift 6. So most of nowadays hydrodynamic simulation, they input a uniform UV background in the simulation at all scales. So it's a time-dependent field, which is everywhere in the simulation and is turned on at redshift 6. You can do better, you can do a better model, and you can do a local photoionization field, which is what people have started doing in the last years. And this is an example of it. This is showing you a slice of the local universe. This will be the Virgo cluster, Fornax cluster, and our own local group, in which we are calculating the UV energy depending on the position of the galaxies. So when you are in a region, where your gas is in a region immediately surrounding big cluster or big groups, it gets immediately ionized. So these orange areas are ionized gas. But when you're far away from sources of ionization, you remain neutral, okay? So this is what people have started doing recently, and it's very promising. Okay, so you have your gas, it cooled down in the simulation, it forms stars, you have a UV background, and now your stars evolve according to their mass. So you can compute a stellar evolution, And what happens in general when your stars are massive enough, they can explode as supernovae and release metals into the surrounding gas particles. So your gas particle gets metal enriched. And this is also what we call stellar feedback. In general, stellar feedback can be either energy from massive stars, or can be given in the form of stellar winds, or as in the case of supernova explosion, if there is a lot of energy released into the surrounding gas that surrounds a supernovae. And there are two main ways in which this stellar feedback is implemented: kinetic or thermal. In the thermal feedback, what you do in the simulation is just you give an extra heat to the gas around a star-forming region. And instead, when you have a kinetic feedback, you kick your gas particles. So both of these things have the same goal, which is to regulate the growth of your galaxy. So you don't want your gas to cool infinitely. You also want the gas to stop cooling at some point, stop forming stars, okay, in order to reproduce a nice-looking, good-looking galaxy. And finally, another element you can have in simulation is black hole feedback. Not all the simulation have black holes, some of them do. And when they do have black holes, the way of doing is typically you seed a black of mass of about 10 to the 5 when you have very dense and very cold gas. And then your black hole will start accreting by eating the gas around it. And then when it becomes AGN, it can release energy and can give you feedback by both quasar mode and radio mode. And just before going on the funniest part of the presentation, which is modern simulation, I just want to spend one more word on what is feedback, what we think is feedback. Feedback in general, in simulation, is a process that regulates the growth of galaxies. It's something that we need in order for the gas to stop cooling at some point and to just regulate star formation. So without feedback, you will have gas infinitely producing stars. So it will never form the galaxy that we observe today. And as I say, feedback can be three main things: stellar feedback, AGN feedback, or this UV background feedback. We include this into the feedback because what the UV background does is actually preventing the smallest dark matter halos to create a galaxy on the first place. When you have very small dark matter halos, the UV background prevents gas to even collapse into them. So you're stopping galaxy formation into the smallest dark matter halos. Okay, let's now go to the part which is, I'm going to show you some representative simulations of what people have been doing in the last maybe 20 years. So the first one that I want to start with are this simulation called MAGIC, Making Galaxies in a Cosmological Context. They've been run now 10 years ago, in 2012. They've been run with a Lagrangian code called gasoline. And the main goal of this simulation was to reproduce just one simple basic scaling relation, which is this one, the stellar mass versus halo mass relation of galaxies. This is the semi-empirical prediction, this line over here. You can see that most of the simulation run before, they did not even match that single simple relation. So this MAGIC simulation, to my knowledge, were the first one that actually produced very well resolved galaxy that follow this scaling relation. That scaling relation is pretty important. It tells you what is the halo mass of each galaxy stellar mass. So that's the most basic relation you want to reproduce. If you reproduce too many stars into your dark matter halo, there is something wrong with your model. So what was the physics in this simulation? Well, a lot of things that I already said. Initial conditions coming from cosmology, hydrodynamic solver, star formation rate proportional to the Kenica-Smith law, a UV background radiation starting at redshift 6. We can have metal line cooling. We have supernova feedback, and particularly we have feedback from massive stars before they even explode as supernovae. So this was the key in order for the simulation to actually reproduce a lot of scaling relations. When I talk about scaling relation, I mean all the relations that we observe in the universe, okay? The Talley-Fisher relation, the star formation rate versus stellar mass, things that we can actually measure and observe. So you can see all these lines and points are observations, and all these color dots are the simulation. And so the beauty of this simulation was that with the same set of parameters that could make a nice, good-looking Milky Way, at the same time they were able to reproduce galaxies all the way to the dwarf and to the smallest objects we observe. A successor of this magic simulation are the Ni-Hao simulation, which are numerical investigation of 100 astrophysical objects. So as the name said, these are 100 individual galaxies run again with the cold gasoline, pretty much the same physics as magic. And you can see here the evolution across cosmic time of a dwarf galaxy in this simulation. This is a dark matter density, this is a gas temperature, and this is a star, stellar density. And so you see, particularly in the gas, that initially the gas is cold, and as supernovae explode, they create these hot red bubbles of warm gas. Okay? This is the effect of supernova feedback, is to heat up your gas in the galaxy so that you don't continuously form star, but you regulate star formation. And so this Ni-Hao simulation, they did pretty well at reproducing the all masses of galaxy. Again, this is stellar mass versus halo mass. This is the semi-empirical relation in gray. And all these points are galaxies. These are 100 galaxies. So you see that they follow very well this relation all the way from a Milky Way size object, this one, to a dwarf galaxy object. And you can see in the bottom for representative morphology of the galaxy we produce. A follow-up project has been what is called Ni-Hao Ultra High Definition, which is reproducing realistic Milky Way galaxies. So you can see, in fact, how realistic it is. This is a flyby image of a simulated Milky Way. You can see very well the central bulge, the spiral arms. You can see star-forming region. And this is just really beautiful. Of course, this is a mock image coming from this simulation. And it looks a lot like the Milky Way. Here has a very thin disk. And so all the simulation that I've been talking so far, they're called isolated simulation. Isolated means that you just use the zoom-in technique to produce one single galaxy, but still with cosmological initial conditions. Another example of isolated simulation are the fire simulation. They've been done in the US. They use the Gizmo simulation code. And this is an image of the different morphologies and types of the galaxy. They do a very good job by reproducing a lot of observed relation. And there are a few follow-up projects coming from this fire simulation that you can find on their website, such as the Latte project and the Elvis project. So when we move instead on cosmological boxes, so not on individual galaxies, but on cosmological boxes, the first simulation that really reproduce the whole variety of galaxies and their morphology in a large cosmological box, 100 megaparsec scale, is the Eagle simulation. This is the evolution of a galaxy in this Eagle simulation, which is evolution and assembly of galaxies in their environment. It's a project done by the Virgo Consortium a few years ago now, and they really reproduce for the first time a lot of galaxy within a large portion of the universe. A similar approach, a more recent simulation, has been done by the Illustris team. They use what is called the Aripo code, which is a quasi-Lagrangian code. And as you can see here, they reproduce a lot of morphologies of galaxy, so not just elliptical galaxy, not just this galaxy, but also irregular galaxies. Okay? They can reproduce in a large cosmological box thousands of these galaxies of different masses and different morphologies. And then we have something in between, an individual galaxy and a large box. And these are typically simulation of groups. For example, simulation of our own local group. A very famous example is the CLUES simulation, which stands for Constrained Local Universe Simulation. In this case, we have constrained initial conditions. It means that we use observation to constrain our initial conditions so that our ratio is 0 we have a local group, which is our own Milky Way and Andromeda galaxy, living within the correct environment. So with a Virgo cluster nearby, a Coma cluster, and so on. These simulations use the gadget code, and as you can see, this is a zooming area of our local group. They reproduce very well the Milky Way, Andromeda galaxy, and Triangulum galaxies, and all the satellites around them. A more newer version of this constrained simulation is the STIA one. So the STIA simulation just came out like 2 years ago. It's a high-resolution environmental simulation of the immediate area. Again, they are local group simulation, now run with a different code and different physics, but the idea is the same, is to study in detail the local group, which is the only area in the universe in which we can really see a lot of galaxies because it's near us. Okay, I'm almost going to the end of my talk. The last simulation I want to mention is this ELVIS, which is exploring the local volume in simulation. What they did by using the Gizmo code and the FIRE physics, they went a little bit beyond and they make 12 different local groups. So to have a little bit of statistic on the local groups. You can see here an example of Milky Way and Andromeda in one of these simulations. And okay, so the talk is over for the part about simulation and blah, blah, blah. I would like now to tell you a little bit of how to actually run and analyze a simulation. Because when I was a student myself, I had no idea what it actually meant to run and analyze a simulation. I thought that somebody would just give me data and stuff. So the first thing you need to do is to get CPU time on a supercomputer, which sounds fun and easy, but it actually is quite difficult. You have to write a proposal, demonstrate that you can run a simulation, get your proposal approved on your supercomputer, and when it's approved, send your code, send all the data, get into a big queue, and eventually, hopefully after a few years or months, you have your simulation done. So one of the supercomputers when we run simulations on time is Barcelona Supercomputing Center, and it's called Mare Nostrum. And you can see an image of this supercomputer that I want to show because it's stored in a beautiful place. It's an old church. So if you go to Barcelona, I strongly recommend you to go for a visit to this old church, which has a lot of supercomputers inside. What you then do, once you have a place to actually run your simulation, you need your initial conditions. They can be idealized or better cosmological. Then you can use your favorite code, whatever it is, gadget, gasoline, arepo, whatever. You run your simulation until redshift 0, or whatever redshift is the one of your interest. And then what happens? So the output of your simulation is just a grid, a big file of particle positions and velocities and masses. Okay? So the output of the simulation is just a big file containing x, y, z, and velocity vx, vy, vz of your particles in the simulation. They can be dark matter, gas, and stars. What happens then, well, you can do everything on your own, or you can have what is called a halo finder to do the hard job for you. The halo finder is a tool that can be downloaded freely, for example here, that essentially looks in your simulation output for overdensities, define those overdensities as dark matter halos, and stores for you the dark matter halo property in a file, which we call a halo catalog. So there are a few halo finder that you can use, like one that we always use is Amiga Halo Finder, AHF. You can use Subfind, Rockstar, whatever. The point is always the same. It does the hard job for you. It identifies dark matter halos and galaxies, and it stores them in this big file. It's just columns telling you the first dark matter halo has this mass, velocity, position, and whatever. So you can directly use it and access the halo catalog. And then, of course, there exist analysis softwares, which is what makes our life much easier. One of my favorites is PinBody, that again can be downloaded freely in GitHub. PinBody helps you analyzing your simulation, both embody and hydro simulation. It can make a lot of plot in seconds. It can make rotation curves of galaxy. It can show you the dark matter distribution in your simulation. It can show you a galaxy, face on, edge on. It's a really powerful tool. Okay, what is the future of simulations? Well, the basic idea is to get higher and higher in resolution, to be able to resolve as many physical processes as possible, and at the same time to have enough statistic. So we have at the same time, we want to have large boxes with a lot of galaxies in it. And I think the GPU-based codes are a promising avenue in this sense. They can speed up your calculation a lot. What is the ultimate goal of simulation? Well, the ultimate goal is to reproduce the observable universe, okay? With its variety of galaxy, groups, and cluster in great detail. And while we do so, what we're trying to do is to validate our cosmological model, okay? If we can reproduce a very good universe looking like our own, then we're confident that the CDM is the correct model. If we can't, perhaps we have to rethink about what is dark matter and what are their properties. And I'm going to leave you with this nice flyby into the Millennium simulation, and thanks for your attention.
Okay, questions, comments?
Hi, thank you for your nice talk. Just a quick question about the n-body dark matter simulation. So if I understand, there is no dissipative process at all.
No, not at all.
Okay.
You just have collisionless dark matter. The dissipative process comes in and kicks in when you include gas. Gas feels pressure, and that's you have dissipative processes, and that's why you can cool the gas down.
Thank you for the talk. Actually, maybe could be related with the first question. What are maybe the challenges to introduce maybe self-interacting dark matter in these simulations?
So there are a lot of people in groups that are actually working on self-interacting dark matter. By the way, it's a type of dark matter that interact with itself, as the words say. So it's intimately different than core dark matter. And one of the reasons to introduce self-interacting dark matter, it can solve a lot of the small-scale problem, we say, of lambda CDM. So the challenges that I see, I mean, computationally is not that challenging. The way you do it, you just give a probability to each dark matter particle to interact with neighbor dark matter particles. This is how you implemented it in your code. The problem is that there is a lot of degeneracy with the result of this simulation with, for example, implementing baryonic physics processes. Sometimes the same baryonic physics process that solve the small scale problem of lambda CDM, for example, they resolve the Caspen core problem, you can solve them at the same time using self-interacting dark matter. You can create a central core, and that's nice. So the problem is to disentangle between all these different scenarios. But there are people that are actively working on this, including baryonic physics into SIDM simulation. So it's definitely an avenue for research.
Hello, thank you very much for your talk. I was wondering if is there any code out there prepared to follow merger history of halos? I guess a brute force method would be like to stop your simulation at certain snapshots and then run halo finders and try to identify how the particles evolve, but this sounds a bit too naive, I guess.
So your question is if there is a way to follow the merger history of halos?
Yes.
Yeah,
yes.
that's every simulation ever run has a merger history attached to it. And we can do that, for example, using halo finders. And then the halo finder, what it does, it goes in each previous step of your simulation and it looks at the particles. Each particle has a tag, has a unique identifier. So it looks at the particles that belong to your halo Rashi 0 and you see where it was in the previous redshift. And so it tells you which one were the progenitor of your final halo. So you actually have the whole merger history and the whole mass accretion history of your galaxy. This is something that you can do it alone, which is pretty boring, or you can have a halo finder do it for you. But that's an essential quantity to know, because we want to know how a galaxy has grown.
Okay, because I thought that Halo Finder just gave you the final picture of the solution.
No, the Halo Finder can be run at any redshift you want. And so not only the Halo Finder can do a lot of things, depending on which one you choose and what parameter you give. Typically what it does, the basic computation is it finds halos at redshift 0, he identifies them back in time so that you can build a merger history, but he also tells you what the profile and what the particles are in every halo, so you can follow directly the particles if you want to. It does many things.
Thank you very much.
More questions, comments?
Thank you very much for your talk. I really appreciated the fact that you went through each step, because for me, you know, coming from the theory side, I see the results of simulations, and for me, it's like black magic. So thank you so much for doing that. Maybe you answered this already, and I just missed it, but you said that in hydrodynamic simulations, you also include gas and you model that as a fluid. But then what happens to the dark matter particles there? Do you still have an n-body approach, or?
Oh, yes. So in hydrodynamic simulation, you still have a gravity solver, which is what is used to solve your force of gravity on an n-body set of dark matter particle. And at the same time, you have a hydro solver, which solves the hydrodynamic equation for your gas. Yeah. And then you follow the gas, you see where it goes, you see when it forms stars, and so on. So you have both things. Yeah.
Thanks a lot.
You're welcome.
So I was wondering about how sensitive those simulations are to the size of your particles. So do you expect that if you manage to maybe go below 10 to the 5 solar masses, you will see physics that is significantly different? Or?
Sorry, if you have a 10 to the 5 solar masses dark matter particle, or what's that?
Yeah, so I mean, you said there were certain limits in terms of the particle size, right? So if
so you can run a lot of tests to see what the resolution kicks in and what is the we call it convergence test, to see how safe is your simulation in the physical results. And so when you do that, you typically see that lower and lower mass dark matter particle, which means that your simulation, higher dark matter particle means that your simulation is less resolved. When you have a dark matter halo and input 10 to the 6 solar masses dark matter particle, that's worse resolved than if you put 10 to the 4 dark matter particle. So when you go to lower resolution, what typically happens is that you start losing predictive power, especially in the central region of galaxies. And so I cannot tell you exactly what is the minimum dark matter mass required to be sure about your result. You have to run your exact problem with different resolution level and see where there is convergence. And so compare your different resolution in terms of dark matter profiles, number of halos you get, and see where the results are consistent. That is your convergence level. But typically the resolution of things that we're doing nowadays, 10 to the 4 to 10 to the 5 to 10 to the 6 dark matter particles, is more than enough to look at a Milky Way or a dwarf galaxy.
Okay, thanks.
More questions, comments?
Thank you for the nice talk. Can you just explain me again what are the initial conditions that you use in your simulation? How do you choose them, and at which redshift do these simulations start?
So at which redshift simulation start is a good question, and you can start it at many different redshifts, but of course it has to be a faraway redshift in order for the simulation to have a cosmological meaning. So sometimes we start simulation at redshift 90, sometimes at redshift 40, sometimes, like in this case, at redshift 28. So just for you to remember, half of the time of the universe is redshift 1. So between redshift 90 and redshift 50, nothing happened, pretty much. There was no evolution or galaxy formation. But let's say typical simulation, we start around redshift 50 and evolve to redshift 0. And the way in which we impose initial condition is, so the initial condition is in your simulation is just a grid of particles for which you have x, y, z, position, and velocities. And these position and velocities, we take them from cosmology. So we can translate the CMB temperature anisotropy power spectrum into a matter density. And once we translate this, we know where were the overdense region and the underdense region in the early universe. And we impose this in your simulation. What it means practically is that in this almost homogeneous grid of particles, you don't see with your eyes, but there will be areas that are denser than others. We are talking about a very small density contrast. Typically, a density contrast in the early universe is 1 part every 100,000. So it's very tiny fluctuation. But those are enough to start collapsing structure in some areas.
Thank you.
Any more questions, comment?
Hello again, one more question. How easy is it and how much has this been done to perform these simulations in some type of modified gravity model?
In some, sorry?
Some type of modified gravity model, something that is not GR.
So I don't know exactly the answer of, I mean, people have doing it, trying to run simulation for modified gravity, but I got no feeling of how long it takes or how it's been done, or I have no idea.
No worries, thanks.
Okay, so I think we had a good deal of questions and discussion. So thank you, Oriana. Thank you
Thanks
all
for
for the discussion. I think, no? We have a coffee break? Yes. We have coffee and cookies and everything, and we're back in half an hour, okay?
Now it's working. So we're gonna get started. Please take your seats. So it is my greatest pleasure to introduce you to Professor Malcolm Longueur. Malcolm flew yesterday from Cambridge all the way down here to Tenerife, and he's going to have an intense week with us. Today he's giving this lecture for the winter school, but next week in the Department of Physics building, he will be giving 2 more lectures on quantum mechanics, right? And then, in a week time from now, he will be giving another public lecture in this museum, but for open public. It will be a totally public lecture. Today, he's going to be speaking about 100 years of astronomy, astrophysics, and cosmology. Please.
Thank you very much. Can you hear me? Yes. It's a great pleasure to lecture to the school. It's an absolutely wonderful program you've got. What I'm wanting to do this afternoon is things that you may know about, but I'm wanting to look at it from a particular point of view of methodology and the way that things actually happen, so that you can be bold when you're doing your researches, do dangerous things, and they may not work, but it doesn't matter. Some of them will. So it's to give you an idea of the very tortured way in which the great discoveries and the great advances were made in astrophysics, astronomy, and cosmology. Now, this lecture was actually, I prepared this one to celebrate the 100 years of the International Astronomical Union in Vienna in 2018. And so I had to put an emphasis on the international nature of it and why the IAU is so important in making sure that astronomers of all countries can talk to each other. So I'm going to mix up the sociology, the physics, the technology, the theory, all of that. It's all part of the way that astronomy now works. So, here's my thesis. My thesis is the following, that it's the symbiosis between astronomy, astrophysics, cosmology, physics, chemistry, technology, computation, etc., put everything else you want in there, that results in a multidimensional interaction between these cognate disciplines. It is this prime source of the incredible astronomical history of the last 100 years. It's the fact that these people are now mixing up expertise from different regions to address astronomical problems. The nature of discovery in astronomy, astrophysics, cosmology is emphasized in this lecture. But remember, once the discoveries are made, there's a long process of consolidation, converting a breakthrough into a new discipline with significant changes in perspective. It's no good just discovering quasars and get one quasar. That tells you nothing at all until you put all of the great discoveries in their context. And that's, of course, what many of you are doing. You're taking the science and actually advancing it to do new things. So let's do this. Now, if you want more details of much of this, it's in my book here, the Cosmic Century, History of Astrophysics and Cosmology. It was published in 2006, but that's got much of the stuff I'm going to tell you about today. Well, this, since it had to be international, I have listed here great discoveries, which I listed in my book. I went through my whole book and wrote down what were the great astronomical discoveries, and then interleaved that with discoveries in physics to show you how the interaction between the two disciplines occurred. So I'm not going to go through all of this because you will see, oops, we moved ahead too fast. Come back. There we are. Right. I get quite excited giving this lecture, so we may flip-flop every occasion. So anyway, here is up to 1919, and the reason for that is that the IAU was formally founded in 1918. But in physics, they're in yellow, and in astronomy there. But this just gives you an idea of the sort of tools that you had available to do astrophysics and cosmology as a function of time. So you will see here we've got the formulation of Boltzmann's Gibbs statistics, validation of Maxwell's equations, Michelson-Morley experiment, all in these dates here. Then we've got the foundation of the Astrophysical Journal, which I like to date as the beginning of modern astrophysics. astrophysics, because at last astrophysics became a respectable subject with its own major journal. And by astrophysics, that meant spectra. So before that, most of the work is imaging, one or two great pioneers before that, but Astrophysical Journal was definitely the journal of spectroscopy. Then we've got the beginning of the construction of the 100-inch telescope. We've got black-body radiation, the discovery of quantization, harvest sequence, radio transfer, dating of the Earth by radioactive data. And then we've only got the discovery of quanta by Einstein in 1905, special relativity, and so on. So it really goes on. Here we are. We've got, again, Emden gas spheres, the first proper equations for stellar structure. Validation of the molecular hypothesis only came in 1907 with Perrin's great experiments. Then we've got discovery of white dwarfs, and so on. You can see, I'm not going to read this all out. It'll get very boring. But you can see that there is the development in parallel between physics and what was happening in astronomy. But notice there's no quantum mechanics. Right? Quantum mechanics only became proper in 1925, 1926. I'll be lecturing all about that. That was really torturous and horrible, but it was great, a really great story. But what it meant was that you were using the old quantum theory, which was completely wrong. Right? You couldn't do things as I'll discuss in that other lecture. So that was what was happening. Now, in 1919, technology in computing was the following. Astronomy meant optical astronomy. There was nothing else that you could do at that stage. It was dominated by developments in telescope and instrument design. So, for example, by that time, one had the commissioning of the 100-inch telescope, which really was crucial. Ritchie-Chrétien optics for large telescopes, and the construction of fast spectrographs. These were the things which enabled the discoveries of the 1930s to take place. There was the continued development of photographic plates as the recording element for imaging and spectroscopy. And the use of computers meant people. So they were people who did the sums for the great surveys of the stars and so forth, and that again led to some of the rather great fundamental things. So when the IAU was then founded in 1918, here are the numbers of adhering countries who joined in it and how it developed until 2015. And you'll see there's a steady increase from the pioneering 8 countries until we've got here, now we've got almost 80 countries, and it's exceeded that now. So what it's showing is that astronomy became an international effort throughout this last period. Here is now the membership of the IAU. Now, this is a good approximation to the number of professional astronomers there are working nowadays. So we start off at the beginning with 207 astronomers worldwide who'd signed up as part of that. Now we're way up here, around about 15 or 16,000 people. So it's a gigantic development of the field. Now, you'll notice it's rather flat up to around about 1960, and then things start to take off. So, let's see. Here's what happened. The most important thing that happened was the expansion of the observable waveband for astronomical observation. There were huge developments in technology, in particular radio electronic techniques and access to space. There was the development of detector techniques, especially thanks to the semiconductor revolution, major advances in physics and cognitive disciplines, advances in computing power, and the impact of the introduction of high-energy astrophysics and general relativity as tools for the astronomers. These were the things which suddenly, around about 1950, 1960, started to hit the scene. And that all led to a huge increase in the volume of discovery space. So if we look at now the discoveries chart, here are the number of discoveries according to my analysis. So back we go again. Sorry. Here's the diagram again. If I just to go backwards, here we are. Let's see. Here is again the number of discoveries, and there's the discovery. There's the introduction of the Astrophysical Journal here, and then we've got this steep increase as the optical astronomy really started getting going. Here's the discovery of quantum mechanics in the diagram. Then we've got the war years, which resulted in a decline in the activity because people were doing other things. Then we've got the introduction of radio, X-ray, and gamma ray astronomies. So that's what really happened. Now, in the interwar years, then, this is, just to give you an idea, things were just gradually developing steadily. There's no point in going through this, but you will see that the flags are very, very widespread. You know, many different countries are now making fundamental contributions to astrophysics. And here we go on. You know, I cannot read this all out, or we will be here till midnight. You don't want that, right? But this is just showing that these are the fundamental things that were beginning to take off through that period. We've got, again, we'll come back to some of these topics just in a moment. But again, it makes the point that the discoveries were made on the international scene. It wasn't all the Americans, which they like to claim. It wasn't that way at all. It was done by a large number of very bright people who were the lucky people who had jobs in astronomy to do things. Now, when I was writing my book, I had discussions with William McRae, who's a very clever cosmologist, and he wrote me this letter. People don't realize that before, say, 1916, astronomers simply had no idea what the inside of a star was like, and had no idea how to find out about it either. The speed at which Eddington transformed the situation was incredible. Now, again, Eddington is one of the heroes of this story, but it was not a straightforward path. And here's an example. His great insights into the theory of stellar structure were not gained without a considerable struggle. The physical data needed to construct the stellar models were not available. And just to give you an example, Eddington, in his great works, it's a great book, no question about it, but here's what's in it, and beware. For example, what Lee and Mestel refer to as the hair-raising approximation that the radiation pressure is a constant fraction of the total pressure throughout the star. My God. Right, now, you all know that's wrong, right? But that was the approximation that he made. And so it was no surprise that the subject of stellar structure provoked heated debate. And if you look at the reports of the Royal Astronomical Society, the vicious discussions, I'm surprised they printed it, but it was true. They were really very, very great debates. But see, the interesting thing is that Eddington was lucky. And that was because the form of the mass-luminosity relation for stars is remarkably independent of the processes of energy production and the opacity law. Right? You know, you need luck. And that's just the way that the physics worked in that particular case. And again, you've heard many examples of this in the lectures that you've been hearing, how you need a bit of luck to make this work. Then, of course, we've got the Einstein's universe. Once general relativity was formulated, as you've been hearing, Einstein really realized he had the tools to derive the first fully self-consistent model of the whole universe in 1917. But at that time, the expansion of the universe hadn't been discovered, and so you had to make a static universe, and so introduce your great friend, the cosmological constant, right, into the calculations to provide a static model. Well, Alexander Friedmann took the Einstein equations and then solved them properly, which included expanding solutions as well as the expanding solutions. Now, the key realization in Friedmann's papers is that isotropic world models, which are the zero-order approximation, which you all know and love and can do on the back of an envelope, right? These isotropic models had to have this isotropic curvature everywhere. And there was no reason why the universe should be static. So that's why the Friedmann's great papers really are crucial. But again, Lemaitre and Robertson independently discovered the same models. And here's Lemaitre, who got essentially the Hubble's law in 1927. Howard Robertson found the same answer in 1928 and actually made the first estimate of Hubble's constant of about 500 kilometers per second per megaparsec. And then Hubble, whose name is associated with Hubble's law, clinched basically the argument. But here's his original picture, and you can see there's not a lot of stuff. And his great contribution was to actually estimate the distances. The redshifts had been obtained by Slipher, Vesto Slipher. He got round about 21 of the redshifts needed for the law, and then Hubble added in the distances. But even by that time, by 1929, they were going further. And in fact, in this picture, this is how far they'd got. This is with Humason and Hubble's version of 1934. And now you're going way, way out using the fifth brightest galaxies in cluster to establish the results. Well, I think you all know about that. But again, it does depend upon assuming that these are standard candles. Then Franz Witte discovered the missing matter in clusters of galaxies in 1933. What you don't learn is that he based his estimate on the measurements of 8 galaxies. Would any of you trust that nowadays? You know, you don't need Bayesian statistics to tell you that's pretty crummy, right? To be able to do it. But he got the right answer. And that was the thing that, you know, if you've got such a gigantic velocity dispersion, then you can't be all that wrong. So again, the figures are here. 500 was his estimate of the Mice light range, which is compared with 3 in our own galaxy. And Zwicky got it right. There's no question about that. Now, I want to look now at the impact of the Second World War upon astronomy. And this is to say that we're actually benefiting from technologies that many people might not desperately approve of, but that's what happened. Okay, so let's just have a look at that. Now, the impact of the Second World War really was one of the major items associated with the opening up of the electromagnetic spectrum. Major advances in radio techniques and access to rockets from above the atmosphere. Now, because of the huge contribution that physics made to the war effort, the governments realized it was a good thing to invest in pure science. And again, the expansion of the astronomical activity was largely thanks to the support of the military agencies. There was the beginning of the scientific electronic computation. There was, but also the idea that astronomy was big science. In other words, to be at the forefront, you needed to have things like the 200-inch telescope in order to be able to be competitive. And these all contributed in many different ways, unexpected ways, to astronomical discoveries. And here's what Bernard Lovell wrote when he was summarizing things up. The astronomers adopted an approach which was utterly different from that deriving from the pre-war environment. The involvement with massive operations had conditioned them to think and behave in ways which would have shocked the pre-war university administrators, who regarded, you have to be able to do it with your hands and build it in a shed. But that's not, the people had been dealing with massive operations, huge budgets, and doing things very, very quickly. All of these facts were critical in the large-scale development of astronomy. Well, just here's one example. After the war, Martin Ryle and other people went to Germany and pinched as much high-quality aerials and so forth as they could. This is an example of 2 of the telescopes that they actually brought, the Würzburg telescopes, which they just went and put on. They took about 100 train wagons of equipment from Germany and brought them back and then distributed them among the scientists for free. But what was obvious then was that the German technology was way, way ahead of the British technology. So, for example, they brought back a lot of high-quality radio antenna, like these Würzburg telescopes, low-loss coaxial cables, and surplus quality radio equipment. And one of the things when you look at the history of the development of radar is that you could tell which was a German signal and which was a British signal, because the British signal will be have a messy beam pattern and the German one had a beautiful Gaussian pattern, right? Just because the engineering was better. But all of that came back and then used for the development of radio astronomy. Also, the German V2 rocket developments were absolutely a fantastic piece of engineering. And these V2 rockets really worked. And again, Werner von Braun really was the central person in the technological development which was going to enable people to go into space ultimately. So here's what happened. There was the tremendous development of rocket technology, and in 1946, Lyman Spitzer wrote the RAND report outlining the future possibilities for space astronomy and proposed a program of space missions. Well, that was on the table, waiting to be picked up, and then things accelerated with the launch of Sputnik in 1957. NASA was founded in 1958 in response to the fact that the USA was falling behind Russia in rocket technology, and Yuri Gagarin's space flight really shocked people in 1961. Then the space race began in earnest, which also meant that there was the availability of rockets to launch science payloads as well. Another interesting thing is that there was a NASA conference on experimental tests of general relativity in 1961, which informed the future development of space tests of general relativity. And at the same time, quite independently, the first Soviet gravitational conference took place in 1961 as well. So they were all onto the idea that you could actually do astronomy from space. Well, another example of what you get from involvement in military is the discovery of the gamma ray bursts. I think, as you all know, the gamma ray bursts were discovered as part of the surveillance program for atmospheric nuclear tests. You had these satellites up there, and you could get a gamma ray signal if someone had naughtily exploded a nuclear weapon in space. And again, here are the pictures of the Vela 1 and the Vela 2 and Vela 3, and here are the examples of gamma ray bursts. So that was a tremendous bonus, which came directly out of the Defense Department's initiatives. Here's another one that people don't talk about, but this, and NASA denies that this actually happened, but it really did happen. Oops. This is the KH-11 Keenan satellite and the Hubble Space Telescope. The KH-11 Keenan Surveyor satellite was built by Lockheed and launched with CC detectors in 1976, 1 year before the final approval of the Hubble Space Telescope program. All right? And the interesting thing there is that, of course, I was on one of the working groups for the Hubble Space Telescope from the very beginning, and we kept hearing rumors that actually NASA had built one already, but nobody ever talked it. And you will find that NASA denies its existence. If you want fun, look up KH-11 Keenan satellite on the web, and you'll see what happened. But anyway, we know what happened because they showed the pictures that were taken, and the CCDs were not developed to the state for astronomical use until 1977. So it's an interesting place that the reason that NASA was sure they could build the HST was that they'd done this blooming thing already. All right? So that's why there's a 2.4 spare mirror lying around, right? Because that was designed for the military purposes. Anyway, this is jolly serious stuff we're talking about, but nonetheless, astronomy benefited from it tremendously. The same is true of the infrared detector revolution. Now, I was personally involved in the HST problems and also in this, because, as you know, infrared detector arrays are fantastic beasts, and those on the JWST are tremendous developments. But the important thing is that in the optical, we've got dust absorption, which obscures interesting bits. In the mid-infrared, the dust is emitting because it's heated up. And then there's this beautiful little gap where the dust isn't transparent, and you see the real universe of stars underlying the whole business. But The interesting thing is that when I was director of the Royal Observatory in Edinburgh, we worked with the contractors to the Ministry of, to the Defence authorities in the USA to get access to their infrared arrays. Because no individual country commercially could actually afford the development costs of that. So we were able to get the first infrared array cameras on the UK infrared telescope, and it was absolutely mind-blowing. What we saw. We just saw pictures like this, free of dust and so forth. So that's just to remember that you know, whatever your views about involvement in military programs, many things which we take for granted wouldn't have happened without them. Now, the 1960s is what I call the miraculous decade. Now, if you were asked what date you would like to be born in this period, or start doing research, the year would be 1963, when I started as a graduate student. That tells you I'm ancient, right? Okay. So, but that time, everything was about to explode. And it's one of these times which you're just lucky for these things to happen. But, you know, there's a message, you know, go for the places where things are going to be very exciting. So here's what happened in the 1960s. And it's an incredible list of things. So we've got the beginning of stellar structure computations. We've got the measurements of the 5-minute solar oscillations. Sandage's much improved work on Hubble constant, the semiconductor detectors for infrared astronomy with Johnson and Lowe, the discovery of the Hayashi track, which was only 1961, the horizon problem in cosmology, the flatness problem in cosmology, Earth rotation aperture synthesis, discovery of X-ray sources in the X-ray background, and the exponential decay of the light curves. And that's only 2 years. Right? It was really a terrific. Here we go on. The discovery of interstellar molecular lines in the radio waveband, the Kerr black hole solutions, discovery of quasars, accretion models as a source of quasars and galaxies, the problem of the cosmic helium abundance, discovery of the cosmic microwave background, Lyman alpha clouds as cosmological probes, the barrier asymmetry problem, detection of far infrared sources in the Orion Nebula, and the theory of superluminous motion. You know, this is all happening in a fantastically short period of time. Here we go on, development of VLBI, the violent relaxation of clusters of galaxies, baryogenesis in Sakharov's rose, gamma ray astronomy, discovery of radio pulsars, discovery of BL-like objects, the thermal history of the universe in detail, silk damping, 2-point correlation from junctions of galaxies, and then the Hawking and Penrose singularity theories. Right. That's all happened in 10 years, right? And so, you know, those of us who were at the time, it was absolutely just discovery after discovery after discovery. And it was all thanks to technology. That's what was doing it, enabling us to open up the new wavebands. Now, just one or two notes, because high-energy astrophysics came about, you know, as a big surprise. It involved totally sorts of astronomy that were totally unfamiliar to the classical optical astronomers. Well, you know, they didn't believe that we were serious astronomers at all. We couldn't even draw our maps of the galaxy correctly, got their coordinates wrong and everything. All that sort of thing the radio astronomers had to learn how to do. But it ended up with a completely different sort of things. Here's the origins of, again, the radio astronomy. We've got here, again, Karol Jansky, who did the first detection of the radio emission from the galaxy, and then Groth-Reber, who produced this map of the galaxy with his homemade radio telescope in the 1940s. But then things really got underway after the war, because certainly within the UK and Australia, not so much in the United States, there were huge efforts in radio technology, principally for radar, either in planes or on the ground, and so forth. And so the physicists wanted to understand what was going on, and so that was the beginning of this huge expansion of radio astronomy. The observations soon established the existence of large populations of galactic and extragalactic radio sources, and a whole pile of new challenges came up. Again, this is the famous picture of of Cygnus A, the brightest radio source in the extragalactic source in the northern sky. And then Jennison and Dasgupta at Jodrell Bank showed that it had, by this double structure, again, a very simple model for where the radio emission comes from. So the fact that this very distant massive galaxy was a radio source, the brightest star in the sky, immediately you knew, good, if you go deep in the radio wave band, you'll pick up things at cosmological distances. So that's what I was doing. I was taken on by Martin Rao. He said, you do cosmology with this stuff. So that was my project, PhD project. Now, again, the reason things were so different from the optical waveband is that the radiation was synchrotron radiation. And that meant that there had to be two major components of the universe: huge fluxes of ultra-relativistic electrons and large-scale magnetic fields. But both of these required energies associated with about 10 to the 6 solar mass in the material to be ejected from the galaxy. That's serious high-energy astrophysics. How do you do it? Well, 1963, the first quasar was discovered with the Parkes telescope. Again, you all know about that. This is 3C273, and here are normal galaxies at the same distance as the quasar. It was really a staggering discovery. And when I started in 1963, Martin Ryle told me, go and find more. So I discovered quasars number 4, 5, 6, and 7. Nobody remembers who discovered quasars 4, 5, 6, and 7, but they were all there in the radio catalogues. And in particular, I discovered 3C9, the largest redshift quasar at the time, redshift of 2, which again was profoundly important because that meant you would redshift then the Lyman lines into the optical spectrum. And that was great fun. I hadn't a clue how important that was when I did it. I was just doing work for Martin Rao, you understand. Now, they had the first symposium about this was in 1963, and here's what Tommy Gold said at the closing dinner. He said, everyone is pleased. The relativists who feel they are being appreciated, who are suddenly experts in a field which they hardly knew existed. The astrophysicists for having enlarged their domain, their empire, by annexation of another subject, general relativity. So it really meant that astrophysics had to change, and you had to suddenly understand general relativity seriously, and not just as a sort of ornament in theoretical physics. Well, this is Martin Ryle, who was my supervisor as well as doing this, and his great contribution was to get aperture synthesis in practice working. It was a fantastic technical challenge because interferometry stuff, really tough. Those of you who are interested in that sort will know you've got a great challenge to make interferometry really work. But the first Earth rotation aperture synthesis telescope was this machine at Lord's Bridge, and there are the first maps that came off the computer. I was in the computer room in Cambridge when these maps came off the printer. And we just said, oh my God, it works, right? Because you've got to get all the phase compensation, you've got its stability and everything. All of that has actually been successfully done. And of course, that's nothing compared to what you can do now with the VLA. So they're the same diagrams with the VLA, and you can see, this is the way it happens. And things like ALMA are doing the same thing. And then completely by chance, the pulsars turned up. And that was another very, very major innovation in 1967. Tony Hewish built the array here, and the objective was to find strongly scintillating sources, which were generally quasars. So this is a powerful tool for discovering quasars. And then, suddenly, Jocelyn Bell, his research student, discovered something very funny, something scintillation when it ought not to be. So here's the original discovery record. Sorry. What we've got here is, again, the record, and here's the strange signal, and there's interference. It's a tractor, right? But what happened was that this was at the same sidereal time every day. So unless the tractor driver knew to live on sidereal time rather than time, it couldn't happen. So that was soon shot down. But the key point was that this object was rather far away from the sun. And you expect very small scintillations through the screen of the solar wind when you're out at very large distances from the sun. And so that was very strange. Something peculiar had to be happening there. Well, here's Jocelyn with the discovery records of the first pulsar, PSR 1919. And again, we've noticed the subtle differences between that and the interference. Well, it really is one of the key discoveries of modern astronomy, because what it told you is that relativistic stars really exist. You know, they had to be neutron stars, and they, as you know, require an understanding of general relativity to understand their stability. So this was absolute proof that general relativity was relevant to stellar evolution. Now, at the Brighton IAU in 1970, Yuzha Shklovsky, I'd been a year in the Soviet Union working with all the great Soviet scientists. And Yuzha came to me and I said, introduce me to Miss Bell. I want to meet Miss Bell. And he said, Miss Bell, you have made the greatest astronomical discovery of the 20th century. Now, discuss. Right. But it certainly meant that you could no longer neglect the effects of general relativity in understanding the operation of the stars. Around about the same time, superluminal motions were discovered. And here's one of the most beautiful early examples of what happens. What we've got here is the VLBI image of two blobs in a quasar. And then it was followed over the next 3 years. So that's 62 light years. That's 68 light years. And next year, 77 light years a couple of years later, and 87 light years 3 years after the beginning. And that's what's called breaking the speed limit in a really serious way. In other words, these are superluminal motions. Wonderfully, Martin Rees, one of my colleagues in Cambridge, had actually predicted what would happen. That if you've got these jets moving out from the source at a small angle to the line of sight at a very large but subluminal velocity, then you can get this happening. This is looking from above, and I'm sure you've all seen this, but it's... this is an example of where we've got, in this case, you'll see this is the years observed on Earth after 1 year, 2 years, 3 years. But because this is coming out at 0.98 times the speed of light at an angle of 11.5 degrees, then this is what happens. The radiation almost, the beam almost catches up with its own radiation. That's what does it, all right? And so you can see here, this is going at 5 times the speed of light as observed in that model. Now, this is again one of the great results of the VLBA, the Very Long Baseline Array. And you know, this is a diagram which I think ought to be better appreciated. This is the result of 20 years observations of these sources. And you will see that we've got values of apparent expansion up to about 32 gamma 32. That's seriously close to the speed of light. That's gamma 1 to 1 minus v squared over c squared to the half. So again, this just shows you what some of these extreme objects can do in producing these jets. Then we've got the birth of X-ray astronomy. Here it is, this sounding rocket experiment, which was launched by Giacconi and his colleagues in 1962. And they discovered, as you see here, here's the background radiation, here's the Scorpius SCO-X1 here, there the moon is there. They were actually trying to find reflected X-rays from the moon. And that wasn't there, but they discovered this instead. And here you can see we've also got a background radiation as well. So these were the great discoveries in 1962. And this really was the beginning of the X-ray astronomy. The next big event was the Uhuru satellite, launched in 1972. Here it is with Bruno Rossi and Marjorie Townsend. That is the Uhuru. That's it there. And you can see the richness of the sky that we've got here. How are we doing for time? 10 more minutes. So? 10 more minutes. 10 more. I will have to speed up. Sorry. Right. And of course, they discovered the pulsating X-ray sources, which again was another key discovery for modern astronomy. And that, as you all know, is due to, again, accretion onto the compact object of the mass drawn off the primary star. And then after that, with lots of effort, one was able to find, again, the objects which are the neutron stars, here down in this part of the diagram. There's the upper limit to stability, and then here all the others which contain the black holes. Again, the story gets better and better. This is the picture, which I'm sure you all know, of the orbits of infrared stars about the galactic center. And the important thing about this is that the way these observations were made was with using adaptive optics in order to be able to get sufficient resolution to actually see the motions. If you just put an ordinary telescope without adaptive optics, you're not going to do very well at all. But you can see this one's done the complete orbit around the galactic center, and you get masses which are over 10 to a million solar masses. The other way that one can again look at what's going on in these systems is to use the X-ray lines. And here is an example of an accretion disk about a black hole. And what I've indicated here is again the accretion disk with a last stable orbit about it there, and then we have to take into account the effects of the gravitational plus relativistic Doppler shifts on this fluorescent line of iron to see what we expect. And when you do that, there's what you get. You expect this distortion away from a single line into a long tail, which goes right down to, again, very low X-ray energies. At this point here, you're getting radiation coming from the last stable orbit about the black hole. And there it is. There's what's observed in this case. Now, what always slightly worries me is this is the best case that one's discovered. It's quite difficult to find other similar ones, but the X-ray astronomers are working on it. That's what, again, a good example. But then, of course, the most recent thing is the Event Horizon Telescope, which, again, is a spectacular example of how the technology enables you to actually get extremely high angular resolution. There where the telescopes are. Again, it's a whole world experiment at very high frequencies. And again, the technical problem is preserving phase coherence at the very high frequencies, which is a real big challenge. But that produced that picture. And if you do the computations of what you expect the objects to look like, they look exactly like this. It's a fantastic experiment. I never thought I'd ever see this happening, but this is really right down in the core of M87. And then X-rays from clusters of galaxies. Well, you've heard so much about that today, about how the clusters and that are such powerful tools. I don't need to say much about that, except that when you've got images like this of a couple of clusters of galaxies colliding, absolutely fantastic, because you're using so many different technologies here in order to be able to get the dark matter from the gravitational lensing, and here's the hot gas here, and then you also got the counts of galaxies as well. So it's the way in which the different wave bands are interacting nowadays, and you've got to actually match your program to what is becoming available. Well, again, just quickly, gamma ray astronomy, just the birth of that. Again, there are all the various projects that they contributed to this, and it really has opened up completely new aspects of high-energy astrophysics. Again, getting up to the highest energies, we can use things like, this is the HESS system in Namibia with these telescopes, and of course there are spectacular ones that you'll be seeing tomorrow when you go up to see the telescopes up there. This is again opening up the new way of studying the very high energy phenomena. Supernovae. This is an example of 3C279, where we can see here at the low energies we've got the optical and radio wave band, and that is by processes, accretion disks and so forth. But then we've got the extreme X-rays and gamma rays. Again, most of the energy is being lost at very high frequencies. But again, you cannot do this without relativistic beaming at rather large Lorentz factors. Well, here are the again, the Batsy experiment showing the huge number of gamma ray bursts observed. And what's interesting is this gives you access to large redshifts where these bursts are coming from. Here's a nice picture, which I rather like. They're the short bursts, less than a second, and the long-term duration bursts here. But this shows how quickly you could get to large redshifts with the gamma ray bursts. Here's how long it took galaxies to get out to large redshifts. It took a long, long time. Here's the quasars, which got more quickly there, but the gamma ray bursts gave you access very, very quickly to the large redshift universe. Well, we're getting on. Stars, star formation. And now, this again is coming to the cool universe side of things and life. Again, for me, this is some of the most beautiful astrophysics we've got, looking at the vibrational modes of the sun, the helioseismology. You know, this is absolutely terrific. And because of the splittings of the line, you get a huge amounts of data. This is the dispersion relationship for the frequency against angular degree of the modes of the sun, and it's utterly spectacular. I think these are about 100 times the error bars are shown in these lines. You've got incredible precision in getting the modes of oscillation of the sun. And you can then invert these data to get this amazing picture. You remember Bill McRae told me that you had no way of investigating the inside of the sun. Well, here it is now. Because what this is showing are the differences in color between the smooth stellar model and where there are differences. So for the first time, for example, we've got here the difference between the convective zone and the radiative zone inside the star. And this also contributed in major ways to the neutrinos problem in the sun. Which is the next slide. Again, the solar neutrinos were one of the great problems why they were far fewer neutrinos from the sun than expected. The result here, again, was fully confirmed by the Kamiokande experiments. But as we now know, what was happening was that we were getting the oscillations, or the neutrino oscillations between one form and another, again contributing directly to fundamental physics in this way. In the final snow experiments from the Canadians, they actually pinned down again the three brands of neutrinos that we knew about. Optical UV. I'm not going too fast, I hope, but we're almost there, right? This is, again, one of the great battles of optical astronomy, that you get patchy views of the objects. But what happens is, as you all know, is that the radiation from UV and optical is transformed into far infrared radiation by the re-radiation of the dust. And that's the way that protostars get rid of their energy, as you all know. So it's an absolutely fundamental process for stellar evolution. And you know, this is just I like this. I created this one by pinching bits of data from the Spitzer maps. Here's the oh God, we're going ahead of ourselves. Here's the Hubble Space Telescope image of the Orion Nebula, which you all know and love. And here is the one from the Spitzer Space Telescope. Again, this is run in the mid-infrared wavebands. And you'll see suddenly all of obscuring dust disappears, and you can see where these powerful infrared sources are. You know, it's absolutely transformative. And that's, of course, what led to the very strong case for building the ALMA array, which is an absolutely incredible instrument. You know, if you think of the complexity of doing interferometry and then getting 66 telescopes to talk to each other phase coherently, that is seriously technology. But the results of that is quite staggering. You know, this is again one of the very first images of a protoplanetary disk about XXXIII, which is absolutely mind-blowing. This picture, you're actually seeing there what had thought to be happen of the disks and the gaps in the disk about the protostar. And again, you can see how well this is doing. The whole solar system would only occupy the inner part. So if I put that's our solar system on the picture of XXXIII. Do it again, since we can. Right. So you can see that we're beginning to get to angular resolutions where we should be able to observe the processes of planet formation within these disks. Then there's the exoplanet story, and that again is quite mind-blowing. Here is the discovery of 51 Pegasus. One of the best things that I did for Cambridge was to get Didier Queloz to come to Cambridge. It cost me a bucket of money, but we got Didier to come, and he's now leading a tremendous program on the origins of life. We got a big grant to study now really seriously the technology that we need to understand. We're building a little lab which will actually imitate the surfaces of planets, and then we will look at the chemistry that goes on within it. So as you know, there was a tremendous rate of increase of discovery of exoplanets. Here they are here. This only opens now, but the Kepler mission really has done a fantastic job in discovering them. And the staggering thing to me is the gigantic diversity that we're discovering. You know, there's no typical exoplanet. They're all over the place on all of the diagrams. So it's a very exciting area of research. And just to show how difficult it is to do the chemistry, here is an example of a spectrum in the millimeter waveband. Good luck, right? You can see the tremendous range of the of species that you can actually now detect in the wavebands here. Now, of course, the big challenge is to dig out of this the ones which are really important, and then to analyze what happens to the chemistry to produce the molecules of life. So don't memorize this, but you can see the sorts of chemical pathways that are now beginning to be investigated in the laboratory to find out how it is that we could get the key, what we call the amino acids used by life. But how are we certain? So one of the great things we will be doing with things like the JWST is actually getting the spectra of extrasolar planet atmospheres. But even if you detect it, how do you interpret it? So here it is, just a very nice diagram which shows the sort of things that you might have. So you can see there, here's the Earth, right? We've got O3, O2, H2O. Here's again examples of what might be present on different types of planetary surfaces. And so the question is, how do you actually determine which of these are actually going to be suitable for actually potential life forms to exist? So again, there's lots of beautiful challenges in that area. Now, you've been doing cosmology all week, so I don't have to say much about it at all, because you're much more expert than I am in all of this. But it was discovered by Penzias and Wilson by accident in 1965, and then these wonderful results from, first of all, W. Mac, and then the Planck things. All of you will be living Planck experiments during this week, quite rightly, let me say. And really, these have provided the benchmark for contemporary cosmology. Now, I would emphasize that for me, it's the technology that made this possible that's terrific. And the fact that there were two competing Italian and French teams meant that they were both trying to be better than the other. Don't quote me on that, okay? But it really was a competition. And they ended up with identical answers. And that to me just shows the sheer quality, not only of the instruments, but the data reduction, which has been absolutely terrific. Well, you've seen this far too often, so I won't show it any longer, right? And you've seen that 1,000 times. It's an absolutely fabulous thing. And you've seen that 1,000 times too, how to invert the distribution of the CMB to actually discover the mass distribution in these structures. And you've seen this thousands of times too, right? Showing you the six primary things, the 6-parameter model that fits. That is incredible, that it should work so well. And then you've got the derived cosmological parameters. And again, it is quite mind-blowing. When I started doing cosmology in 1963, my supervisor, I had two supervisors, Martin Ryan and Peter Shaw. And Peter Shaw said, there are only 2.5 facts in cosmology. Right? One was the sky is dark at night. Right? The second one was probably the universe is expanding with the Hubble's law. And the third one is maybe the radio source population is evolving with cosmic epoch. That was the half one. He was being too modest. It was clear. I did, for my PhD, the sums properly, and nobody had bothered to do them properly before that to show what a tremendous divergence there was between what was observed and the proper theoretical predictions of the models. People had forgotten that the cosmology kicks in at redshifts around about 0.2, 0.3, and not at 1. By 1, you're gone, right? So again, it's the sort of thing. Just try to find the problems that people haven't done properly. And then you've heard more. Oh, you don't need to see this because you're bored with this by now. So many of these, and you're bored with this about the universe being geometrically flat, and the redshift of reionization. And I like to put it, the dark matter is a difficult problem. I find the dark matter an annoying problem. I think we ought to have solved that one. And I'm very unhappy that we haven't. We've done something wrong and stupid, I think. But anyway, you are the people who will solve it, not me. I'm way past it. But you guys will solve it. I'm absolutely confident you will. If that's bad, the dark energy is very difficult. If you look at the equations, the cosmological constant only kicks in at large redshifts, and my goodness, you're doing all the right things of looking at the Euclid future experiments and the polarization experiments, but it's annoying. I often wonder if it's not the fields that are gone wrong, but whether it's just the geometry that's gone wrong. Because remember, you've got the T on one side and you've got the G on the other side. As one of my friends say, T and G, that we turn it around, G and T, that's gin and tonic. Yes, please, I'll have one. But one's going to have to look at all of these details, and again, it's going to be a tough struggle. And then, of course, all the independent S's you heard this morning are looking promising, that they're coming together quite successfully. And again, one of the good things about the way things are done nowadays is you can actually believe the errors. It's a tremendous change of philosophy to actually go to the rather rigorous Bayesian and all sorts of other contemporary techniques to take out, once you've taken out all the systematics and so forth. So it's a very exciting time. And the accelerating universe, well, I always think, my goodness, the CMB is so much more convincing than this. But I'm not allowed to say that, or I will get myself into deep trouble. I didn't see it. Okay. And then finally, the gravitational waves. Now you've seen what it is. You've seen this picture many times, and this is a fantastic technological achievement. They're unambiguous. I never thought I would live to see this. It is just so tough. I'm sure you know about this again, the detectors across the United States. But look particularly at this picture here. This was the sensitivity which had to be achieved to have a hope of detecting the pulses. And it's 1 part in 10 to the 23. Now, that's what I would call high precision. Right? But what's even more impressive is this next picture. And here it is, the way in which the sensitivity developed over the years to make that possible. Now, you'll see that they've got the basically right shape here. This is again 202, coming down to here, getting better and better. And then eventually you got back to the present one where you're down at the sensitivity level. This is the most impressive picture for me about the whole story, because notice the timing, 2002, and then you got a positive result in 2016. Most funding agencies would have given up. And I asked again the leaders, how did you do it? What was the trick to keep the funding agencies on site? And they said, well, we had good guys running the NSF. We had good guys, people who actually cared, and realized that although it took a long time to get there, but once it happened, of course, the result is quite utterly fabulous. And here it is. There are the pictures that everybody knows and loves. You look at that picture, you say, oh yes, that's a gravitational wave. Totally and utterly unambiguous. You don't have to do a sum. It's just as the right thing. And then the discovery of the coalescent binary neutron stars. Shortly after, when I gave this lecture in 2018, there were all of the coalescing binaries making more massive black holes. And when I looked at the most recent version, here it is. Right. Absolutely staggering. Right. You know, there it is. You can start now doing the real astrophysics. The samples are very large samples. So it's 6 o'clock, and here's my last slide. Right. So what is the secret for having a happy astrophysical life? Here it is. Oops, no, complete blank. That's new technology instrumentation. That's what makes us believe all the things you've been talking about. It's the fact that the technology is fantastic and it's being supported. Whatever aspect of it you're doing, push for that. With that, we will find many new things. New ways of doing astronomy. You know, many people were skeptical about gravitational waves. Precision observation, so that we're now in the epoch of precision cosmology. When I started off, it wasn't that way. It was rubbish, right? But now you've got extremely good values and convincing values of the cosmological parameters. The extensive database and computational facilities. That's going to be absolutely mandatory that we keep advancing these to make things happen. Things like the SKT, capitalizing upon discoveries in other disciplines, particularly in the particle physics area, which you've been hearing all about. Cutting edge theory. Now, some of my colleagues would say that theory has contributed nothing to cosmology. It's all the observations that do it. That's not true. But there is a sense in which you need to now have absolute precision theory, because if you're not determining parameters at the level of less than 1%, your theory's got to be better than 1%. So again, I don't believe my colleagues. You've got to keep going at it. But again, it's got to go hand in hand with the observations. And then the last theory are very important. Imagination. Do something different, right? Do something unexpected. Take risks, not too many risks, or else you will become no good. But take 1 or 2 risks and see what happens. Perseverance, keep at it, and most important, you need a bit of luck. Thanks very much.
Thanks so much, Malcolm, for this great review. So we have some time for questions. So please, okay, I see that Ariana is raising her hand. Just give me a second.
Thank you very much for the wonderful review. I have a bit of a doubt. Like, I studied myself as a young astronomer doing gravitational waves, and then I gave up because I was bored of waiting and waiting. So it took me only 2 years to get bored. And then I moved to a field of simulations. But just like the discovery of gravitational wave, they took quite a few decades to become a reality.
Yes.
My question is, how long do you think, or how long should we wait for dark matter to be found with direct experiment and direct measurements before actually starting thinking to the worst? We made something wrong, there is something that doesn't work. Because there's been already quite a few, decades.
Yes, it's...
should we start getting worried? What's your point of view?
Yes, it's almost unanswerable, the question. And you will notice that the costs of the experiments we're talking about are very, very large now. If you look at something like the gravitational wave experiment, if you look at the ELT, if you look at the SKA, all of these future-looking projects, they're almost at the limit of what can be funded. So I think the answer is that when the money runs out, you'd better get out of the field. That's really the answer. It depends upon the funding agencies being absolutely persuaded of the importance of what you're doing, even if you get negative results. Politicians don't like negative results. But yeah, and that's why I think the gravitational LIGO experiment has been fantastically lucky to have sympathetic administrators. But it's a judgment that everyone's got to take. When is it worthwhile persevering, or should I go and do something else? It faces every researcher. So you've just got to get good and sympathetic mentors, supervisor. I always tell students, remember, choose a good supervisor. don't just take any old person. Make sure you get someone who's got a good reputation for really helping students.
Thanks. Great advice.
More questions for Malcolm? The other way around. We go this way.
Thanks for the awesome talk. Just a kind of more of a personal question. Which either mission or project are you most looking forward to seeing the results from? So like SKA or Euclid or any of kind of projects from the next couple of decades? Are you excited to see?
Yes, all of them.
Right.
It seems to me that it's maintaining this breadth of attack upon the difficult problems is the way to actually make progress. I'm very excited about what's coming out of the JWST. You know, the redshift limits are going up. There's one possible redshift 17. And you know that is really opening up incredible this. So because of the way they've used the fuel, I think we'll get 10 years of the JWS2. But it seems to me that all of these other projects that we're talking about, they go through a tremendous scrutiny. Because we're talking about such large amounts of money nowadays that you've got to be absolutely, totally and utterly convincing or you won't get the money. I'm sorry to talk about money, but in the end, I've spent a lot of my life actually getting large sums of money to do big, big projects. And you've got to actually get extraordinarily good cases nowadays and then keep at it. So that's it. But all of the ones that you've mentioned and lots of others, the SKA, everything else, the new giant telescopes in space, we just got to keep at it. That's the rule.
More questions?
Hey, Malcolm. So one thing that I find fascinating about history of science, and this is what you're doing, is to look at things where we have big failures as opposed to big successes. And I was wondering two things. Are there any interesting big failures in this history that you think are worth pointing out, and so which? And what we learn about? And then also, in your personal experience, were there any times where you made something, took some really wrong turn, and how do you recover from that?
Yes. Well, it depends. It becomes controversial answering this question. The lists I produced are the positive ones, as you say. But what would you say about steady state theory? Right? For example, was that a huge mistake? I got myself burned many times in battling. I was the piggy in the middle between Martin Ryle and Fred Hoyle, and that way you grew up quickly. Very, very quickly because of that. Personally, I've made some bad mistakes. When I was working with Martin Ryle, we worked on a relativistic theory, and I did my relativity wrong. And that was a bad mistake. What it really meant was I didn't understand the relativity properly. And that was the beginning of a process whereby I essentially relearned the whole of my physics in order to make sure I didn't make mistakes like that again. But I had not come through the standard Cambridge route, where people were well trained. I came from a completely different background. And so when I started lecturing in Cambridge, I had to relearn everything my own way and lecture it that way. So I think it's an important message for everyone, that everybody understands physics and astrophysics differently, and that you will have different pictures in your mind of how it is that the physics works. And what you will find helpful is to find your way of understanding difficult things. And that's the way to also have fun doing it, but also to make sure you don't make mistakes. So there's nothing. There are good mistakes and there are bad mistakes. And if you do make mistakes, make good mistakes. Because the good mistakes will actually teach you something very important that you hadn't understood before. And that's a good way of learning. I don't know if that's an adequate answer.
So we're going to have now the last question. I'd love we could have more questions yet, but there's yet a new talk coming after this one. So here is for you, Paco.
Thank you. Do you believe in dark matter and in dark energy?
I believe very profoundly in dark matter. As I say, the dark energy is such a gigantic problem. I just wonder if there's something that's not quite right at some fundamental level. As I say, I often wonder if it happens that the problems with the geometry rather than with the physics, the physical processes. But again, that's just hazarding guesses.
Do you think the discovery of the Higgs particle is something which, having a scalar field, would support in some way believing in dark energy more?
Oh yes, no, that's a great great achievement. That and indeed we have that. What I'm most excited about now is being able to reproduce negative pressure equations of state in the laboratory. So we've got, when you look at the ultra-cold atoms and Bose-Einstein condensations, you can actually, in the laboratory now, on a desktop experiment, begin to get things which look like negative pressure equations of state. And that may well give us clues about what we need to do to be able to rationalize how you might be able to get something like a cosmological constant.
Thanks so much, Malcolm. I love we could continue, but now we have a public lecture from David, and so let's thank Malcolm again.
Thank you. Thank you.
And let me stress again, he will be giving 2 lectures this week in the physics department, and also a public lecture here in a week time from now. Thank you, Malcolm.